So this is a section of the notes on the nature of light. We start here because to understand how light interacts with materials, for example, if you want to use a laser for welding or cutting or other applications, then you need to understand how light interacts with materials. And what we're going to do is we're going to, in this section, look at the nature of light, so the ways in which light can be described, and we'll look at three different ways in which we can describe it. We can describe it first of all as a wave, we can describe it as a ray, and finally as a particle or a photon. So we'll start off with waves. Hopefully rush through this because most of you will have been at least partially introduced to the idea of what a wave is. Based on the principle of superposition, we can make any shape of wave that we want if we add together the right combination of harmonic waves, by which I mean pure sine waves or cosine waves. So the harmonic wave is always the starting point. If we understand how they behave, then we can get a good idea as to how any waveform behaves. So we can think about the wave as it's travelling through space and time, and if we take a snapshot of the wave, so it fixes in time, at some fixed time, we've taken a kind of a flash photo, if you like, of the wave. Then we can look at its spatial qualities. We can look at things like its wavelength, and also its phase angle, the angle that it's offset from zero. And we characterize that wave using wavelength, but we can also characterize it in terms of what's called the wave vector or the wave number, depending on whether we're dealing with scalar or vector quantities. The other way we can think about this is to look at a fixed point in space. So we just look at one point in space and we see we measure what happens as the wave goes past us. Okay. So in a fixed point in space, we do the same thing again. Only now what we have is between the peaks we have a time interval, and that time interval is obviously going to be the period, or tau as it's given here. And similarly, as we had for the wave vector, then we can also think about the period in terms of its frequency, either linear frequency or angular frequency. This is angular frequency shown here, obviously. So pure sinusoidal waves, special case, because we can characterize any waveform, any periodic waveform, using a combination of those harmonic waves. They're characterized by a number of different parameters: the wavelength, the period, the phase angle, and the velocity. And one of the things that waves should do is satisfy the wave equation. So here is the wave equation, and it relates the variation of that wave, its amplitude phi, as a function of x and t. In other words, how does it vary as it travels through space and time? What are the spatial variations and the temporal variations? Okay. So we have this equation for any collection of waves, and the easiest solution for that is again a harmonic wave, where the wave is described as some amplitude term times the sine of a spatial term, kx, and a temporal term, omega t. We can also write this in complex notation, so that we have a e to the I kx plus or minus omega t. And in this course we'll change from one to the other as and when it suits us. Sometimes the complex notation is easier for us when we're doing the maths, and sometimes more intuitive for us to think of sine waves. So we'll just choose whichever representation makes the most sense to us mathematically at the time, but you should look at these as being equivalent. So some things to note about the wave: if the thing involving space and the thing involving time have different signs, then the wave is moving forward, travelling in a forward direction. If they have the same sign, so in this case if it was kx plus omega t, then the wave would be travelling backwards. And we say that the wave is monochromatic because it has one single constant frequency or wavelength. Okay. There's obviously relationships between frequency and wavelength and speed, and so we can rearrange these parameters in the equation for the wave to suit ourselves. We can choose which parameters make most sense for whatever application we're looking at. So we have that the phase velocity of the wave is the frequency times the wavelength. We have the propagation number, or the propagation constant, or the wave number. Let's not call it wave number because that generally means something else. Let's call it propagation number as being inversely related to the wavelength. We have the frequency, linear frequency, and the angular frequency. So we can see that there's a relationship between all three of these. So if I talk about the wavelength being a long wavelength, so if lambda is big, then that means that the frequency will be low. So again, sometimes in the course of these lectures I'll refer to wavelength, sometimes I'll talk about frequency, but I'm going to use them almost interchangeably. So high frequency, short wavelength; low frequency, long wavelength. The phase of the wave, as already mentioned, the phase is the offset from zero. So instead of just being a pure sine wave, we have the sine of our x and thing involving x and t plus some offset angle, here referred to as epsilon. The phase difference between two waves looks at the difference between their relative phases. So the two extremes are when they're out of phase, when one wave is at a peak, the other wave is at a trough, and they're 180 degrees out of phase, or pi radians out of phase, or they can be in phase where the peaks match up. And in this example here, what we've got is a small difference in the relative phase between the two wavelengths, the two waves, sorry, and you can see that that phase shift is given by pi over 3. So the equations for those waves, A is sine of x and B is 0.4 times sine of x minus pi upon 3. So different amplitudes, same frequency or same wavelength, but one is shifted along the axis with respect to the other to give us a phase shift of pi upon 3, 60 degrees. And when we have that, we say that A is leading B because we have minus pi upon 3 here, and we refer to B as lagging A by pi upon 3 radians. Another important property, especially if you're dealing with lasers, another important property of light is its coherence. And the coherence means that if you have lots and lots and lots of waves, then those waves will stay in phase as they travel through space and time. Okay. So spatial coherence means that waves from different points on the source will stay in phase. So let's imagine we've got some surface here, and that surface is giving out light. So here's our wave coming from that particular point, and the wave which is coming from this particular point is going to stay in phase with it. So as it travels out, not really drawn that very well, but they should be in phase. Sorry. So if they stay in phase over the whole surface of that emitting, it's giving out light, it's emitting light, so it's an emitter. If they stay in phase, then we say that they are spatially coherent. Those two waves are spatially coherent. Temporal coherence is if, for example, again, we have some sort of surface, and that surface is again giving out some light. That if we send out some wave at t equals 0, so that's when t equals 0, and then we wait for some time so that when t is equal to some multiple, integer multiple of the period, then again the waves stay in phase with each other, and they're temporally coherent. They're coherent with time. So different frequencies will produce different phase differences. So in other words, if we have two waves of different frequency or different wavelength, then at some points they're going to be in phase, some points they're going to be out of phase, and other points are going to be somewhere in between. So temporal coherence is a measure of monochromaticity. In other words, how pure the light is, how single wavelength it is, or how single frequency it is. Okay. So temporal coherence gives you some information about the narrowness of the range of wavelengths which are coming out. So if we think about just an ordinary light bulb, don't think we have ordinary light bulbs anymore, but when we used to have tungsten light bulbs, you had a piece of tungsten wire, you passed a current through it, the resistance made it hot, it got so hot that it started to glow white, and you got all sorts of wavelengths and frequencies coming out. You had reds and blues and greens and all those added together to give us white. Obviously with the laser, what we're expecting to get is a single wavelength coming out, a single frequency. In reality, as we shall see, that's not the case generally. There is a range of wavelengths or frequencies which come out, and so temporal coherence is gives us a measure of how broad a range of frequencies are actually being given out by the laser. Other thing that we can do with waves is we can add them together, and we can get interference patterns. So we can add them together in such ways as to give us a way of extracting information from them. So if we add the two waves together, if they're out of phase, we'll get destructive interference. In other words, the two waves cancel each other out. And if they're in phase, then we get constructive interference. So we'll get a significantly brighter a brighter signal from the light. The kind of strange thing about destructive interference is if you think about adding light plus light, and you've got destructive interference, then light plus light equals dark, and that always, from a philosophical point of view, I guess, is always a bit strange to me. But we're cancelling. Remember that these ways of thinking about light are not what light actually is. Light isn't actually a wave. What we do is we use waves, the mathematics of waves, to describe how they behave, the behaviour that we see. So it doesn't mean to say that light is a wave, or light is a ray, or light is a particle, a photon. These are just models that we use to describe the behaviours that we see. So if we take some sort of random phase difference, so we have two waves, one with phase phi 1 and one with phase phi 2, then adding them together we just have the sum of sines, and this sine plus sine, 2 cos semi-difference times sine semi-sum. And so what we get is we get some proportional part here, which doesn't depend on omega, so it's omega t, it doesn't depend on time, so this is a fairly constant value with time, and it gives us a modulation which is proportional to the difference between the two phases. And then we have a sine wave, which is what we had before, omega t, and now we have an extra phase term, and that phase term will be the average of the two phases. Okay. So here's an example of destructive interference. So we have y1, our black line, and we have y2, our blue line, and we add them together. They're out of phase, but we have different amplitudes, and so we don't have a complete cancellation. We have the wave is partially cancelled and obviously still in phase with the original two waves. Okay.